Welcome to Rust Belt Science. I'm your host, Maggie Fink.
And I'm Shahir Risk.
This is going to be part 2 of a previously recorded episode that hopefully you've already listened to about the Nobel Prizes, and specifically the Nobel Prize for Chemistry for David Baker. And we want to talk a little bit about some other parts of this protein engineering history.
Yeah.
Shahir, you want to elaborate?
Yeah, so just to recap, I think go back and listen to part 1 because it's really important. But just to kind of recap, we were talking about the Nobel Prize in Chemistry 2024, which was shared between three people. On one side, it was Demis Hassabis and John Jumper for developing an AI tool that can basically predict the protein structure from a sequence, which is a very, very difficult problem that AI happens to be very well suited for. The other half, or 50% of the prize, went to David Baker, who is really looking at protein engineering. How do we take proteins that nature has discovered and kind of expand on them and just kind of come up with new structures and new functions so that proteins can do new things that we have never seen before. And we talked a little bit about the legacy of David Baker and his lab and how pervasive the applications of the work that his lab has done over the last, I would say, maybe 20 years or so, 24 years or so. And but at the same time, while this was happening, there were other groups who were trying to do very similar things. And so we mentioned a pioneer in this field, Steve Mayo at Caltech, who published early on in the 90s about protein engineering, and then in the early 2000s, publishing the first computationally designed enzyme, which he kind of conservatively called enzyme-like proteins. But this was really kind of a big step. How do we take a protein that doesn't have any enzymatic function, meaning it's not something that can carry out a reaction, and then change it somehow so that now it can actually break down something or make something from its basic components? That's a big, big feat. And so enzyme design was really kind of the holy grail. And in the early 2000s, that's what everybody was kind of racing to get to. And there were a few labs working on this, obviously the Baker lab, Steve Mayo's lab, but also Bill DeGrotto at UCSF. And then at Duke University, there was this person, Hama Halinga, as his name, and he was he had developed his own tool for computational protein designs called Dezymer, right, with a Z. And the idea here is that it would be able to take a protein structure and then make changes to it so that it can come up with a new function. And there had been some successes on protein design that came out of his lab, and he was quickly becoming this kind of rising star in protein engineering. He was trained in computer science, but also in genetics, and so he was able to kind of straddle both worlds, which was kind of the new trend in protein engineering. Can we kind of look at both worlds, be the jack of both trades in a sense? And at Duke University, he was able to really use this tool, expand on the infrastructure to bring in more processors, more computational power, and be able to, try to solve this problem of computational enzyme design. Can we take a protein devoid of enzyme function and create that in it? And one of the things that they worked on in the lab, he worked with a couple of graduate students at the time. There were two in particular. Lauren Luger, who was doing a lot of the computational side, and Mary Dwyer, who was doing the kind of the wet lab work, as you would call it. So actually doing the testing afterwards. And they were able to take a protein called ribose binding protein. It's a protein that binds to a sugar called ribose. It just binds to it and then delivers it and releases it. So it has no way to actually change the composition of something. And what they wanted to do is they wanted to modify that protein so that it can make make a reaction happen. And this reaction is a reaction that happens in part of our breakdown of glucose, right? It's called the TIM. TIM is just for triose phosphate, or triose phosphate isomerase, sorry. And this is part of our breakdown of glucose. It's just our natural enzyme that does that. So there is a natural enzyme that does that. We have it. Bacteria have it. That will become important later on, as we will see. And they wanted to see if they can change this ribose binding protein and turn it into essentially TIM, right? The triose phosphate isomerase. And they made a bunch of mutations. They tested a few different designs, and they were able to see some activity. But it was obviously not as good as the natural enzyme, which was always the case with any of these newly designed enzymes. But in a sense, this was the first example of computationally designed enzymes, right? Other than the earlier example from Steve Mayo in 2001. And Halinga and his coworkers published, I believe it was in 2004. They were able to publish this in the journal Science, which is a huge, obviously very high impact journal. And, it was kind of settled, right? In a sense, he had kind of won the race. And based on that, Halinga was able to get a lot of awards. He won the Pioneer Award, which gave him $2.5 million in funding, essentially unrestricted funding, because people were saying, this guy is a pioneer. At the same time, people were complaining about the way that he managed the lab, the way he ran the lab, the way that he treated his students, and just kind of really pushing very hard. And, that can be the case in science of just, pushing your students very, very hard. And really caring about the results more than the well-being of your students. And those were allegations and claims that were happening at the time, but that wasn't too unusual at the time, and it still happens, right? That's unfortunately the case. And so, I think a year later or so, Halinga was contacted by a guy named John Richard from the State University of New York in Buffalo. And John Richard is an enzymologist, which means he studies enzymes, right? Yeah. And he, in fact, studied TIM, that reaction. He spent basically a lot of his life studying this reaction. So that happens in natural enzymes that bacteria have, that flowers have, that everything has. And so he was obviously very interested, what are the differences? How does this work in a different way, like on a mechanistic level, on, kind of like on a fundamental level? Is there differences between this kind of human-made enzyme versus nature-made enzyme? Are there differences? So he contacted Halinga and said, hey, can you send me these designs? I'd like to play around with them. And Halinga kind of ignored it, right? He was too busy. This guy was not really that famous or that important. And this went on for a while where, John Richard was trying to get those proteins to play around with, those newly designed enzymes to play with, but really didn't got ghosted essentially. Yeah. Is that the term?
Yeah. I think so, yeah.
Yeah, that's what happened before the term was the term. Yeah, essentially, because this was back like 2004, 2005. And then finally, Richard was able to talk to kind of more famous people in the field so they can kind of, in a sense, grease the wheels, move things along. And they eventually contacted Halinga saying, hey, is there a reason why you're not giving this guy these enzymes to test? And he said, oh, yeah, no problem. We'll do it. Sent the designs to John Richard. So when Richard's lab got the enzymes, they got the protocol on how to purify them, how to handle them, how to prepare them in the lab, and they did, and they really couldn't find anything. That means they found that these proteins were actually dead. They did not really deliver as promised. So even that slow rate that was described in the Science paper, they really couldn't find it. So they spent at least a year working on this because they said, well, we must be doing something wrong. Right. And that's always, difficult when you have results coming from a big lab and a, groundbreaking experiment and then you're not able to reproduce the results, then you always think that there's a problem with you.
Right.
And I can imagine that that's how his lab members felt.
Yeah. And just how common is it for scientists to, say, hey, can I try that? Can you send me something?
Yeah.
Sharing some of these, especially after they've been published. In my experience, it's pretty common to like, oh yeah, I've got this, I can send it. So this was kind of a red flag from the beginning. Would you agree?
Absolutely. That was kind of a red flag. And it's hard to know why Halinga refused or kind of ghosted him in the first place. But just to answer your question, or to really emphasize the point that you're making, is that it's very, very common, and it's kind of accepted that unless we're waiting to publish the results, right, then things are shareable, because that's kind of the supposedly, at least, the culture in science. It is collaborative, and we should be sharing resources. If I made a strain of bacteria, or piece of DNA, or a gene, or a protein that I've used it and I got what I wanted out of it, I published it, and you're interested in doing something else with it, then it's commonplace for us to do, even if it's actually covered by a patent. So if it's covered by a patent, then the university actually owns part of it. And what they do is it's actually a fairly simple transaction. They do something called an MTA, material transfer agreement, where they're like, they define what you're going to do it for.
Which you have done.
Which we have done before with, whenever there's any kind of patents or anything like that. So this is an invention. We're going to share it with you, and we're going to define exactly what you're going to do with it, and what you can't, and what kind of credit you're going to give us, and so on. So this is fairly commonplace. So it's you can't go into people's minds and actually look at intention. So we don't know why Halinga was not interested, whether he kind of thought that this was not important, and he had his sights on something that's more important, because obviously it was, kind of this rising star in the protein engineering world, or whether he somehow knew that something was wrong.
Right. But regardless, kind of maybe a reason to start to be suspicious, especially when they were unable to get those results.
They were very much unable to get those results. And, they later on talk about how the proteins were prepared in the lab, may have been a little bit different, but ultimately, they basically said, they came back to Halinga's group and said, hey, we have tested them many, many, many times, and we regret to inform you essentially that these are not working. Now, at the same time, and this is something that I think is a little bit, I don't know if sketchy is the right word, but I felt like instead of Richards just going back to Halinga and saying this in private so they could kind of figure it out and saying, hey, what am I doing wrong? He copied the editors of Science, and even the journal of Science, right? So to alert them. And, I guess you're within your right to say that, because then you are basically alerting the journal that published the work and saying, hey, I'm not getting the same findings as this person in this way. It's not just like my word against yours. I have some evidence to back this up. And then now it's not unusual for things to work in one lab and then not work again, right?
Yeah.
I mean, science is kind of finicky, especially when you're working at the edge of discovery. You are at the forefront. You are at the edge of the precipice here, and everything's so delicate. Everything has to be so controlled, and everything has to be, that sometimes people make mistakes. And you say, okay, well, I thought that this is what we had, but, oh my goodness, like, we made this mistake, People are not perfect. None of us are. And scientists are no exception. We have checks and balances, in a sense, where we have, you have to do this many times. So, if an experiment works, you have to do it again. And if an experiment doesn't work, you do it again. Like, I mean, that should be how it is. If it doesn't work, you do it again, because you may have just made a mistake. And if it works, you also have to do it again, because you may have made a mistake, right? And so you always kind of distrust yourself. And I think maybe that's not what happened with the Halinga group. And so normally this kind of stuff is a dispute that would be kind of, as the professor, you are what's known as the corresponding author. Mm-hmm. You are the one who's responsible for everything, and you take responsibility for the results that you publish because your name is on it as the main author, the corresponding author. But what Hellinga did is that he went after his graduate student, the person, Mary Dwyer, who was actually testing these. Mm-hmm. So she had already moved on from the lab, graduated, got her PhD like 2 years earlier, because all of this was happening in 2008. So this was, 3 or 4 years after everything was published. And I think 3 or 4 years after she had left the lab as well. And he asked for a meeting with her, and her current advisor, postdoc advisor, kind of got a little suspicious because Hellinga was kind of starting to get a reputation at the time, and said, I'll go with you. And at the meeting, he basically accused her of making up the data and just completely threw her under the bus. And that was probably, like we want to talk about red flags. There is no, there's no going back from that.
Yeah.
So instead of kind of taking responsibility for it and saying, well, where did we go wrong? Let's go back and figure it out. He basically said, you are a fraudulent person and you made stuff up, which she denied. She said, this is what happened. And then later on, as, things kind of got into light of everything, Duke University got involved and started investigating the whole thing and investigated Dwyer. And eventually Dwyer was cleared of all wrongdoing. But then later on, she went on record saying that, these designs didn't always work the same way. So sometimes they worked better than others. And she basically said that Hellinga was pushing her to publish the best data and throw away the bad data.
Yeah.
And what do we think about that in science?
That is not something you should do.
No, that's absolutely not something you should be doing, right?
Not
I mean, if you do it 9 times, you get great results, and 1 time you get a bad result. Okay, that's a different story. But when you do it 5 times and you only get 1 really good result and the rest are kind of mediocre or garbage, that's not really, that doesn't tell you anything. No. And I think that's essentially what Dwyer claims happened. And by the way, this is all documented in a Nature News article called Designer Debacle. And I encourage people to read it. It was published in 2008, May 9th, 2008. So check this out because it's kind of a really crazy story. Mm-hmm. Because normally when you have bad results or wrong results, you go back and you say, we're going to retract our work. Right? We thought something was happening, but it's not happening. But I think the fact that this was such a high profile paper, and because it had been such a huge breakthrough in a field that was kind of like expecting this and waiting for this for 50 or 70 years or more, ever since we learned what enzymes were, people wanted to design them from scratch. And, and then on top of that, blaming your students, right? Yeah. Which is kind of that's a major, no, you don't do that.
Yeah.
You don't do that, right? And you let investigations take their course. Doesn't mean that graduate students don't do fraudulent things, right? And put their advisors in bad positions, but directly going after that person and, pushing for it, for her to, basically, to be the bad guy essentially is not what you do.
No.
And so there were consequences, of course. And the consequences initially was that they had other people in Hellinga's lab try these designs to see if they worked, and they realized that they don't really work. And they claimed that the activity that they saw, the action they saw, was from impurities. That somehow, because they used bacteria to make these designs, to make these proteins before they test them, that there was background, that they didn't purify their proteins well enough, that there was impurities of the natural enzyme that the bacteria make, right? That still doesn't make sense because of the way the data actually come out. It could explain some things, but it also doesn't explain everything. So the jury's still out on whether, even after all these years, it's been almost 10 years now, 20 years now. Oh gosh.
Yeah.
20
Ooh.
years now. Ooh, yeah. I'm that old now that I'm like, skipping decades. But it's been almost 2 years, and the jury's still out whether it's an honest mistake, a dumb mistake, or an intentional misleading. And those two are very different. So that was one of the consequences, is basically they ended up retracting the paper, basically saying, we take it back. There were actually two papers. They said, hey, yeah, we screwed up. We messed up. And but because of Hullinga's actions and going after Dwyer, he was also investigated by Duke University, and the NIH, the National Institute of Health, that had given him the Pioneer Award, basically banned him from funding. So he basically doesn't really get funding anymore. And Duke University decided, you are not going to have any more graduate students. That's it. You are not a good advisor. And so that's kind of what happened, is a bit of a falling from grace, and and meanwhile, other groups like Baker's group, who just won the Nobel Prize in 2024, was working very hard on actually making enzymes work. And in 2008, right as all of this drama was going on, Baker's group publishes two papers, and they have them checked by other labs to make sure that they actually work, so that there's no bias, and they work in this lab and that lab, and in different hands, as they say. So that was kind of the story. And as it turns out, I actually knew a lot of the characters, because just how connected I am to the protein engineering field. But also, a few years before all of this happened, I actually graduated from the Hullinga lab. So he was my PhD advisor. And, I think it's easy to go after people and say they were evil and they were, tyrants. Obviously, his style of pushing people was kind of unacceptable at times. He's a brilliant person in many ways, very creative in terms of his problem-solving approaches. But as evidence came out, the pushing the results and not doing careful science became more important than well-being of the students in the lab, and also just doing careful experiments and doing things right, as opposed to fame and fortune.
Yeah, I think
it's a story for all of us.
Yeah, scientists are just as human as anybody else, who will blur the lines of what's good to achieve something.
Yeah.
So, we had talked about sharing this particular story.
Yeah.
And talking about these kinds of issues in science, the fraud and retractions and what all those things mean. Scientists know it happens, and we kind of don't like to talk about it, because a lot of people already don't trust science.
For sure.
So to admit that we have a problem with misconduct and fraud and mistakes that have serious consequences, even if they aren't intentional, is kind of like, oh, do we admit that to the public? But I think it is important that we say, there are flaws in the way things are currently done, and that opens up dialogue about what can we do to fix it and prevent this from happening to the level that we see it happening sometimes.
Right. You're absolutely right. And I think, like any industry or any field, there's always going to be what do they call them? The bad actors.
Yeah, bad actors.
Bad actors, bad apples, right? But I don't want that to be an excuse. And I don't think any one of us wants that to be an excuse for, basically rampant misinformation or, and in fact, this is what retractions are for. So that you can say, sorry, we made a mistake. And there are a lot of just honest mistakes.
Yeah, there's retractions that are just, oops, we
messed up.
We messed up.
And by very famous people as well.
Yeah.
And they don't always just kind of fall from grace, because they actually, they're applauded for correcting their mistakes.
Yeah, because they value the science more than the glory of having a paper published.
So then there's kind of a bit of a difference here between making an honest mistake and then owning up to it, taking the right responsibility for it, and not throwing people under the bus.
Yeah.
As opposed to the other side of it, which is fraudulence.
Yeah.
And, the culture of blame in a sense. So can you tell us a little bit more about that?
Yeah. So I did a lot of research for this topic because I really wanted to make sure I had a good grasp on how the scientific community defines these things and what are the actual stats and things like that. So there is, retractions are when, like you said, somebody, a scientist will say, we're going to take this article back, and they might completely remove it or they might correct it and say, we need to correct some numbers. The claim we made is still the same, but we want the data, publish the wrong data or something. Or maybe the retraction is none of this study is correct.
Right.
And that doesn't mean that it was fraud. For some reason, a mistake was made. So, that happens. And I think scientists are happy that happens, that retractions can be made. However, when there is misconduct and fraud, that's the real problem. And I have the definition. I'm going to read a definition.
Read the definition.
This is the definition of research misconduct from the National Science Foundation, the NSF here in the United States. There's really 3 components that could qualify a paper being considered research misconduct. So you can fabrication, making up data or results and reporting them. So just pulling something out of your butt and saying these are the numbers.
Awesome.
Yep. Falsification. So this is either leaving out data, which is kind of what you were talking about in the Halinga lab, omitting the data, or manipulating the research process without good cause. So modifying the way you conduct the experiment to get the numbers that you want. And not really reporting that or explaining why you would do that other than to get better numbers. And then plagiarism, using somebody else's ideas without giving appropriate credit, which I think that's pretty well understood. You don't do that.
Right.
And I have some other stats about just how many papers are actually retracted.
Oh, okay, cool.
Just so listeners can get an idea of, this is a problem, but in the grand scheme of things, how common does this happen? So the retraction rate, which includes both misconduct and honest mistakes, is just over 0.2% in 2022. So a couple of years ago.
That's 0.2%
of all the papers.
So that's like 0.2%. It's like 2 in every 1,000.
Yeah.
2 papers in every 1,000 paper.
Yeah, are retracted.
And that were published in 2022.
That was 2022's numbers. Okay. However, this is 3 times higher than in 2014. So this has increased.
Yeah. So it was less than 1 in 1,000. But let's say it was 1 in 1,000.
Yeah.
Right. And then it became 2 in 1,000.
Just reaching over 2.
Yeah.
Yeah. So it has increased, and there's different reasons for that. And just to again reiterate, this is not fraud.
Yeah, necessarily, right.
But necessarily. This is just papers that have been retracted.
Yeah.
In 2023, more than 10,000 research papers were retracted.
Wow.
Which seems like a big number. But when you think about how many papers are published across all disciplines, a lot of these numbers are pretty broadly encompassing fields of study. So not that many.
Not that many, actually, yeah.
When you put that into perspective.
Right.
But some of the consequences of these papers being retracted or being published and then later retracted are pretty serious. I have a few examples that people might, one in particular people might be really
familiar
with.
Yeah.
That the effects of this paper being published and then later found out to be fraud have had huge ramifications for our culture.
Right.
So Andrew Wakefield.
Yes.
Andrew Wakefield.
Yes.
For some people might immediately recognize his name. He is the scientist and doctor, I believe.
He's a doctor,
Yeah.
a medical doctor.
In 1998, published a paper linking vaccines to autism.
Right. Or like some sort of additive in vaccines. Is that correct? I forget.
I think that is the nitty gritty of it, but that is, vaccines cause autism.
Right. That was his claim.
And
this came out like in the Lancet, right?
Yes, which is a really prominent medical journal. Like not, this is
big publication. Okay.
So he claimed there were links between measles, mumps, and rubella, the MMR vaccine, and autism. And people were like, wow, that's crazy.
Mm-hmm.
And then it wasn't too long after that, a few years after that, people started to say, I don't think this is true.
Yeah.
We have some concerns about the data and how the data was collected.
Right.
And as it turns out, there was some huge conflict of interest in Andrew Wakefield's research.
Juicy.
He was working on an alternative vaccine that would remove this, that didn't have this additive agent that claimed was part of the link to autism. So by publishing a paper that said this causes autism, I have a better thing.
That's going to make me money. Yeah.
So I think he was reportedly stood to earn about $43 million per year from this.
So for people who say follow the money when it comes to vaccines, like this is a prime example of why this guy published this garbage.
And it was absolute garbage.
It's absolute garbage. And it's because and here's the thing. That's the other thing that really kind of ticks me off. Sorry, here's the thing. It grinds my gears. Here's the thing. This guy never said that vaccines cause autism. He was talking about it because he was actually coming up with a vaccine.
Yeah, right.
But he became kind of like the champion of anti-vaxxers to say, oh, well, all vaccines cause, or I'm just not going to get a vaccine at all because there's this one paper, and that somehow there was a conspiracy to shut him down when we actually know that he stood to gain a lot of money from it. So I would encourage anybody who is an anti-vaxxer to do exactly what they tell everybody, which is follow the money.
Yeah.
There it is.
And just to be clear on this podcast, we are not here to
tell people, we're not here to judge people or tell people to go get a vaccine or not.
Doctor, exactly. And there's lots, lots of reasons why people would be hesitant to do that. And I think those are fair and should be listened to.
Yeah, absolutely.
For the record.
Absolutely.
But I think it is also fair for scientists to be able to show people this, up until then, people were vaccinating their children, and we were not having this issue of vaccine hesitancy. And because of this, we've had lots of outbreaks of some pretty serious diseases in the United States that previously were eradicated.
Like measles, mumps, and rubella.
Yeah. Go figure.
Yeah.
So, like I said, this paper was published in 1998.
Yeah.
It was not retracted until 2010.
Wow.
So this was allowed to be in the Lancet, this very prestigious medical journal, despite people bringing concerns only a couple of years after it was published.
Right. So you're saying it takes a long time sometimes for things to be...
It can take a long time for these articles to be officially retracted.
Yeah.
I mean,
we've seen it with the Hellinga.
The Hellinga, it took several years.
Yeah, 4 or 5 years. Yeah.
I have a couple other interesting articles that I won't go into the stories of them necessarily, but there's a website that if you are curious about retractions, it's called Retraction Watch.
Oh, a really good one. Yeah.
It was co-founded by some journalists interested in keeping an eye on this type of thing in science, and so it has a lot of data and some statistics for you, but. The consequences of Andrew Wakefield's situations are pretty obvious.
Yeah.
And a lot of these big papers that do end up getting retracted, they're big papers because they have a huge impact and the claims they make are big.
Right.
So, one of the biggest papers that has been retracted, and it was just retracted this year,
Yeah.
Do you want to guess what year it was actually published? Do you remember?
So it was retracted this year, and we are in the year of 2024.
Yeah.
I forget sometimes.
Yeah,
as
sure.
we
That's
record
okay.
this. And let's see. I'm guessing it's going to be a shockingly big number. 2018.
No.
No.
Do you want another guess, or you want me to tell you?
No, just tell me. Yeah.
So this article was published in 2002.
Gasp. Oh my God.
So over 20 years.
I literally gasped. Holy crap.
Over 20 years, this paper was published in Nature.
Yeah. So another high profile, very prestigious. Yeah.
And I'll read the title of this article.
Read the title.
And then I'll explain it. And people might be familiar with why this is another big one. The pluripotency of mesenchymal stem cells derived from adult.
Okay.
So basically this paper is showing that, or a claim to show that you could take bone marrow, essentially, and they could be stem cells.
From an adult.
Yeah. So, and if the year rings a bell, 2002. At that time, there was a huge debate in the United States about using embryonic stem cells for research.
Right.
And so people were saying, hey, look at this paper. You don't have to use embryonic stem cells, because there's a lot of conversations around the pro-choice, pro-life.
Right.
Using those embryonic stem cells.
Of course.
So this paper came out, and people were like, look, we don't need to use embryonic. We can use adults.
Right.
And now come to find out that paper has been retracted as of this year because of fraudulent data.
Fraudulent. So this was fraud.
There was misconduct in the research.
Yeah. So this was not like, oops, we made a mistake. Sorry. This was like somebody.
It was determined that there was
intention.
Yeah. Well, I don't know if
it was malice already, but it was
research misconduct.
Somebody messed up.
And it took 22 years for this paper to be retracted.
Wow.
And it has been cited by other research articles almost 5,000 times.
5,000 times. So people have built their research arguments on it 5,000 times at least in the literature.
So, the impact of this is huge.
Absolutely.
And it was just retracted this past summer.
Right.
Some of the other top papers that have the highest number of citations, so researchers using these, are in the thousands, and some of them continue to be cited after they've been retracted.
Wow. So that's just lazy. Like you're citing something even after it's been retracted. Right.
So clearly, when this does happen at this magnitude, the consequences are really big.
Yeah.
Whether it is culturally big with the case of the vaccines and these
and healthcare too,
these cultural questions around embryonic stem cell usage.
And also in this show, we're not advocating for one or the other.
No, just stating that was a conversation at the time that this article came out. I vividly remember that.
Yeah.
So I don't know where that leaves the field now as far as some of the ethical questions around that.
Right.
I'm not a stem cell biologist, so I don't know the details about that.
Yeah.
And another thing that why we should care about this and why the public should care about this is because your tax dollars go towards research.
Right.
And if research is being proposed and done on fraudulent papers, that tax money is wasted.
Yes. And I mean, there's obviously going to be, there's always going to be some sort of, waste in any kind of field, right? But this is something that we want to be able to minimize, of course, because then you want to get the most bang for your buck as a taxpayer. So you bring up a very important point that the more we are able to, as scientists, own up to our mistakes, but also being able to watch out for fraudulent or misconduct, fraudulent behavior, misconduct, that's better for everybody. This is not just like some sort of closed group that is just doing its own thing. We're working with
the government.
Government money. This
gives us money.
Yeah.
And, if scientists kind of shove this stuff under the rug and we continue to find out that this is happening, then the government's probably going to cut some of our funding because it's being mishandled and not going to things. So that's another reason I think it is important as scientists to tell the public, yes, this is happening, and then we can have a conversation about it. The other reason I think it's important to talk about this is if you are conducting research on something that doesn't really have a basis, for example, with these stem cells, you're focusing on a direction because a paper came out and was published, and it comes out to be wrong.
Mm-hmm.
You spend a lot of time not actually researching the right thing.
Yes, yeah, it's leading you down the wrong path, and it's wasting a lot of resources on your end, as well as wasting your own time and maybe your own career.
And this is another example of this that happened this year. Is I cannot say how much of it was fraud or just poor,
with lab practice.
Bad mistakes, because I think some of these investigations are still underway. In Alzheimer's research.
Alzheimer's research, very important.
Out of the University of Minnesota, I believe, 2 researchers are under investigation. One for sure, one I don't know if she's technically under investigation right now, but some other research has come from her lab. That the research was manipulated. The data was manipulated in some way, is the claim. And so with Alzheimer's, it's been understood that that's caused by protein misfolding. So
proteins again.
We just got done talking about protein structure, and they need their structure to function. So in Alzheimer's and other, kind of similar diseases, a protein will misfold, unfold, as it were, and then come back together or just completely lose all semblance of a structure that it needs to function and begin to aggregate with other proteins that are doing the same thing.
So just clump together.
And that can lead to these plaques.
That can't be good when you have those things in your brain.
No, so those plaques were observed many, many years ago by, I can't remember his first name, but last name Alzheimer. So,
right. That's where we get the name.
So we know that that's linked to Alzheimer's disease when we see those protein aggregates. But the proteins actually involved, we are now being called into question because of some falsified data about, basically saying, look, we see this protein more in older mice, so this must be
a sign of aging.
But it turns out that is not correct. So this is kind of blown up in the past few months, a lot of these papers, and continue to publish papers based on this falsified data. Now, whether those papers were subsequently, manipulated, I'm not sure, but the claims that they're building on have been determined to be manipulated.
Right. So, and these you're talking about papers that came from the same lab, or you're talking about just papers in general that are built on this research?
I think both. I think they're. I was specifically talking about papers from these particular scientists, I think they've had multiple papers retracted because, they're making claims based on their original fraudulent data. I don't know how much of they've continued to manipulate data in those papers, but then, we have to reevaluate a lot of other research as well that's been built on this claim and say, do we need to rethink some of these conclusions? And these conclusions they're not just happening in isolation in a lab. They then go on to inform how we develop treatment for things like Alzheimer's and so this has kind of been a big scandal recently that I've been following a little bit of, and it's really sad and unfortunate that scientists resort to having to do that.
Yes, absolutely.
And I think there's lots of reasons why it happens, why scientists choose to manipulate the data or, it's really hard to assign motivation and they're just trying to get famous. There's so much pressure in science.
There is a lot of pressure in science.
The publish or perish. And now there's, the growing, the number of publications, and everything has to be awesome. You can't, a couple papers showing something cool that's not really, groundbreaking. People don't care about those either. So you have to be publishing a lot of papers, and they have to be awesome.
So you have to be extra.
You have to be extra. And yeah, I have a quote from a scientist who was involved in one of these scandals, and asked why he did it. And a long publication list is crucial for promotion or for switching institutions to get a better job. But journals prefer studies that show strong positive results, meaning much of a researcher's effort is in terms of career advancement wasted.
Yeah.
So a lot of the things that we do, which is a lot of negative results, doesn't do us any good.
Right. Because
in terms of being able to move up and even not move up, but just get funding to be able to continue to do your research. Yeah. And those numbers of publications are really favored over the quality of the research.
Right.
What are your thoughts on that? And it's coming from a lab that did have something like this, and you said the pressure, you were put under as graduate students.
Yeah, I mean, the pressure on graduate students, and there's something that I think is important to mention here is that power dynamic, because you have a professor or an advisor who has pretty much wields the power because they're paying your salary, they're paying your tuition and your stipend, and so there's already there some sort of power that they hold over you. You are trying to get your PhD, and you can work for 5, 6, 7 years. And at the end of it, if that professor decides, it doesn't always happen, but if that professor decides you're not good enough, all of that time is wasted and you leave with nothing, right? You're back without a PhD. I think it's a little bit different when you're a postdoc, which is the next level on. You already have a PhD, you're working in another person's lab. It's still wasted time if that happens to you, but you leave, you still have your PhD at least, right? Yeah. But then you don't really have the credentials to go on and compete in the job market. So the number of jobs is kind of shrinking, and so competition is higher. There's also this motivation, or this kind of, not motivation, but there's this push for every lab to be a little biotech company. As opposed to doing like this basic science research. There was a lot of people who do basic science research. It's all about like discovery, development, this innovation, this growth mindset, this always pushing the envelope, always doing the next thing, always doing the next thing. Because if you're not, and you're doing the mundane things that are also needed in science, you're going to be overlooked for promotions. You're going to be overlooked for funding. You're going to be overlooked for salaries and positions and everything. And so then there becomes a hierarchy where the biggest, most, whatever, it just snowballs, right? They get the biggest job, and then in the smaller places or whatever, you don't have the resources to try to break through. So you have to be even more creative in a sense. But there is this power dynamic because you are working for someone, even though it's supposed to be collaborative and they're technically not your boss. There's a lot of control over that. And then after that, if you are an international student, then literally your entire life depends on this job that you have, because at any moment, if you are not in good standing with the school, you can get deported. Your status can just be nullified, and then you have to go back, from where you came, and that's it. And this is like kind of your opportunity. So, and I think that a lot of professors know that, are aware of that. Everybody's aware of that, and some use it for good, and some use it for bad. That we're human beings. So that's kind of what I think about it. What do you think about it?
Yeah, I think about more. I'm curious why people who already have the positions of power are the ones committing the.
Yeah.
You've already got it. Why do you need to continue to lie? Right? Because if you look at who's doing a lot of the fraud, it's not the graduate students typically. In fact, if you reading some of these articles, the stories of the graduate students who come into the lab and they're given a project from a previous postdoc or something, and they can't replicate the results.
Right.
Because the person before them had lied, but the graduate student doesn't know that, so they just assume I'm a bad scientist and they quit. A large majority of graduate students who come into these environments that are built on misconduct.
Yeah, they end up leaving.
They end up leaving because
they think there's something wrong with them for not being able to.
And they can't, even if they do have suspicions of something's not right, they can't who do they go to? They
Right.
can't go to the advisor and say, I think something is wrong
Fishy.
here.
Yeah, something's fishy.
Because you don't know how that can go. So
there's no reward for that's the other thing, that the structure of it, there's no reward for proving that someone was wrong. So the work that, going back to our earlier example with Halinga, John Richard and his group, they spent a couple of years on it, spent resources on it, and all they got out of it was to prove somebody wrong, which is not pleasant. No one wants to do that.
No.
But you get nothing out of it.
There's no benefit other than...
Yeah. You don't get to publish bad data.
Right.
Right. And
I'd have a lot of papers if I could.
I think I would have a Nobel Prize in bad data.
So, it is hard to address these issues. There's scientists in here, quoted as talking about when they're trying to report something they think is not even saying fraud, but something's not right.
Yeah.
Journals are not incentivized to respond, and
right.
Because then that puts into question their ability to appropriately peer review a paper before publishing it.
Right.
So they're not incentivized. They're very difficult to get involved in these things, and they usually say, "Oh, it's the institution's problem to investigate their professors." Right. Mm-hmm. And the institutions aren't incentivized to then spend money and resources to
find one of their own at fault.
Yeah. So that's why, this paper I just mentioned about the stem cells, 22 years before it got retracted. Wow. Andrew Wakefield, 1998 and then 2010.
12 years.
Alzheimer's. Some of those were many years. And then, so it can take a long time for these things to eventually get found out. So, that needs to be fixed. How do we come up with ways to not accuse people? I don't think everything, mistakes happen.
Yeah, but to be more rigorous, I guess. Yeah.
And, you and I have talked about this, and I think we disagree a little bit, and maybe we're on the same page since we've talked about it. But, your response has been, well, this is science, the way we do it. It's inherent that these people get found out because of the peer review process, because of the collaborative nature of it. And my argument was, then how come it's taking years and years for these to actually be retracted and be officially called out? So defend yourself.
Defend yourself. I have no leg to stand on. Well, I think you present some really good evidence here of what is a lot of the things that are wrong with what's happening. There could be some motivations. There's obviously the power structure. There's incentives that don't exist for anybody to really blow a whistle, in a sense. I, being who I am, no, that's not who I am at all. I'm more like, I'm tired.
Unvacuum.
I'm more like, I'm tired. I'm tired. But just the optimist in me is saying, this is how science self-corrects.
Yeah.
It's like the self-cleaning cycle where, I, as a scientist, really am interested in good data. So if I find that somebody else is doing something and it doesn't work out for my lab, then I'm going to just call it out, right? But it's very difficult when it's within your own lab and when there is these power structures in place. If you are a woman, if you are a person of color, if you're an international student, if you're a graduate student in any way, or even an undergraduate, there's someone who holds power over you. And, there is obviously, it's important to bring truth to power, but at the same time, you don't know what's going to happen. You don't know what's going to happen, right? So that makes things difficult. Now, when it comes to, there's something that I think is very interesting that you brought up, and that's the increase in the number of retractions. And some could see that as a good sign. Some can see that as a bad sign. I think when you start looking at, I'm just going to use an analogy here that may or may not work. You ready for it? Never. I was born ready, she says. Well, you can look at the number of people arrested for murder, right? And you can say, this year we have more people arrested for murder or burglary, whatever it is, right? And you can say, oh, look, that number has increased from last year. It's doubled since last year. But that doesn't necessarily mean that the number of murders have gone up. Now, with murders, we can actually know because we can go and say how many people actually got murdered. Did that number go up? But when you have something like false claims, you don't know until those murder suspects are actually like, not murder suspects, obviously, but you don't know that, right? So it's kind of like an unknown unknown in a sense. And I don't know if the increase in the number of retractions means that there's an increase in fraudulence. I would tend to think yes, maybe, but just by looking at that by itself. So I'm on your side that I feel like this is a problem and it is an increasing problem, but just the number by itself doesn't tell us that. Although there are some, kind of like predatory journals and other things. And I think that that's been on the rise for sure.
Yeah. I wasn't, this idea of predatory journals and paper mills is, I don't know if that's too in the weeds.
Tell us what's a paper mill.
So basically paper mills sell you papers and say, here, we can change the data, change the disease. You can be the author on it.
Wow.
And you can get a published paper. And they're just completely They're not.
So like you get a paper and you get a paper and everybody gets.
They're completely fabricated.
And it's just based on money. You just pay to publish.
And there's, those same places have paid off editors of journals to make sure those papers get accepted because they have to go through this process, right, of through an editor and all that, and the editor gets to decide. So these places are popping up, especially in specific fields. So it's not as broad as some of the data I've talked about here, but happens a lot with clinical studies and things like that. Just change a few numbers, change the name of the disease, and you got yourself a paper.
Wow.
And you can just get authorship that way.
It's very dangerous.
It is very dangerous. Yeah. And, it would seem like they're easy to catch, but it turns out, I guess, that they get through. I think, I don't remember if I have any exact stats on like how many of these things are paper mills and things like that. But
but I've seen some articles on paper mills and these predatory journals before, and I think this is something that scientists are becoming more aware of, and we want to do something about it.
Yeah, so those are contributing to the retractions and stuff as well, and those are not primarily coming out of the United States.
Where are they usually coming from?
These show up mostly in. These are the countries that have the highest retraction rates, and they're linked to the paper mills and predatory journals. And that's Saudi Arabia, Pakistan, Russia, and China have the highest retraction rates over the past 2 decades. So, a lot of the research that's coming out of the United States is not really falling under this paper mill that gets retracted. Is not,
it's not coming through those channels.
Yeah. It seems like a lot of the big cases of fraud are the United States, but if we're just looking at numbers, that's not coming from the United States.
I see. So the impact versus the sheer number.
Yeah.
Okay.
And I think it's fair to just acknowledge how much pressure people in other countries who don't have the resources that we have in the United States, they're under an immense pressure and resource deplete environment. And so, desperate times, you need to have something on your CV so that you can get a job. And I don't.
So not an excuse, but this is what's happening.
Yeah, I think we need to acknowledge the state of sciences in the United States. We have a lot of resources that other places do not have. And if you're trying to get a leg up, you'll resort to some questionable measures. So yeah, the paper mill thing does contribute. And I think that's a more recent problem that's come up, but it's a little bit easier to tackle too, because it can kind of be pretty obvious. Not, we can use AI to figure this out, right?
That's a problem for AI to figure out.
So I think talking about this, when we were initially talking about this idea, we were a little bit like, oh, should we pull the curtain back and just, we're trying to get people to like scientists and to trust us. And we're like, here, look at all the bad stuff that science has done. And science has done a lot of other bad things, just other than, manipulating data and stuff. But I think if scientists, we can't ignore that this contributes to the problem in science and our relationship to the public.
Right.
And we can be like, yeah, this happened, and we need to do better. We need to develop better ways to ensure that these people have consequences and that the general public knows that this happened, right? I don't know if anybody would ever know that some of these papers are no longer valid research papers if somebody said, did you know that this was actually retracted because of X, Y, and Z? And I don't even know how many people know about Andrew Wakefield's studies being retracted. And the reasons why it was retracted.
Yes.
So I think
and the connection to financial incentive for it, right?
And this Alzheimer's research, and then again this one with the stem cells, that's a huge political issue.
Yes.
When we're thinking about embryonic stem cells versus adults, bone marrow. But this just happened, and nobody's talking about it. And the public, whose tax money is going to us, deserve to know that this is going on. And I hope that just by talking about it, that us and whoever listens can just be aware and also know that science, when it works really, really well. That's why we have a lot of rigorous peer review. That's why it takes years and years and years to be able to be awarded a Nobel Prize most times, because you have to go through a lot of
checks and balances.
And science should be collaborative. And I like something I found in one of the articles talking about how scientists, it's presumed trust. That's why we do share resources. There is this really lovely collegiality that scientists across disciplines have. And then if you are in the middle of something like this, that trust goes away, and you're more skeptical, and you lose the beautiful thing of science. So how do we keep both things? And I think it really comes down to holding people accountable, getting institutions and journals to be more invested in calling these things out, rather than covering them up, because it's not a good look either way. So let's just get it called out so we can restore some of the trust we need with the public.
Absolutely.
So part 2 of we started off with Nobel Prize in the first episode. Super cool stuff. Ending on not as fun stuff. This is
but very important stuff.
This is the reality of science, and
this is the reality of 0.2% so far. Well, but
that we know of. And I think we will find out more in the coming years as people become emboldened to speak up.
And to end on a happy note,
yes, please.
I think this is our chance to recognize all the very, very hardworking scientists whose work goes unnoticed and unrecognized, working in the background, trying to understand fundamental things about our biology, our psychology, our sociology, our everything, and our world, our environment, bacteria, whatever it might be, whose work really sets the stage for these big, big discoveries. And I think that's a shout out to all those people.
Shout out to all the basic scientists, and not like basic, basic white girl like me.
People who study basic science.
Like without, they're trying to answer questions without any application, basically. Right?
And without trying to be flashy about it.
Yeah, they're just curious. And I think that's why we love science. Curiosity. And I think that is why most scientists do what they do, because it is a slog. And it is not a glamorous job, especially for 99% of scientists.
Especially when you're working with bacteria and you come home smelling like bacteria.
Yeah, it's a good time. All right.
Well, thank you.
Note. Yeah.
Thank you for this. This was really enlightening for me, because I really wasn't aware of all the numbers that you mentioned. And I think this discussion is very important for us to know, very important for our listeners to know. And so thank you for bringing that up.
Yeah, of course.
Thank you, Maggie.
Thank you, Shahir.
At the end of our show, we would like to thank you, our lovely listeners, and our awesome audience for spending your time with us. We thank the Notre Dame College of Science and the Indiana University South Bend College of Arts and Sciences. Special thanks to the wonderful people at the Notre Dame Studios. Coming to you from beautiful South Bend, Indiana, in the heart of the Rust Belt. This is Rust Belt Science. I'm Shahir Rizk.
And I'm Maggie Fink.
And we'll catch you next time.